In this video, I want to talk about radiative heat transfer, okay? And when we say that, when I say that, right, I mean I'm talking about an object that's not at 0 kelvins, and I'm really talking about the black body radiation that we've been talking about here, okay? Now, again, just to remind you that this is electromagnetic radiation. So this is like light waves, or it's infrared, or it's whatever. And that depends on the temperature of the substance, right, that's radiating. And the reason that it radiates is that substances are made out of charged particles like protons and electrons. And if you imagine an electron that's here, when it's hot, right, here's this electron, right? Okay, when it's hot, it's sitting there vibrating back and forth between two positions, right? Well, as it moves from this position to this position, the electric field that surrounds all charged objects, this electric field collapses. And that's how you start generating electromagnetic fields, right? Is that or electromagnetic waves, is that you collapse an electric field. Well, the energy in that electric field turns into a magnetic field, which when it collapses turns into an electric field. And that's why they call them electromagnetic waves, okay? So that's sort of concept 0, right? And then concept 1 is that remember that the radiation that comes off is all different wavelengths, right? This is wavelength this way, right? And this is intensity that way. And there is that peak wavelength, the one that it's most probable, the most intense wavelength, and that's related to the temperature, right? So in general, the hotter something is, the shorter the wavelength it puts off. And that makes sense because short wavelengths have more energy and hot objects have more energy, right? Okay. And then this is our formula. This is the power, right? So this is going to be joules per second. This is how much like a black body, a total perfect black body it is. And a black body would be something like, like soot or something like that, right? Charcoal powder is very close, right? And this is sort of a technical thing, right? But basically this emissivity is what that is how good it is at radiating. And some things are good at radiating, some things are not, right? So take a look. Anodized aluminum with that rough surface is pretty good. And by the way, things that are good at emitting are also good at absorbing, right? It's the same. For a given wavelength, this is the same thing. You absorb and emit at the same efficiency. Because if you could, say, absorb more than you could emit, then you'd spontaneously get hotter than your surroundings, and that's not possible, right? But notice that anodized aluminum is pretty good at emitting black body radiation. But if you polish the aluminum, and this is what they do, I think they make telescope mirrors out of polished aluminum, you can polish it and make it just super, super shiny. Polished stuff is not very emissive, right? So think about it, right? If you have a thermos has this inner lining, right? And then it's got a vacuum gap, right? Well, the only way heat can get across that vacuum, it can't convect, it can't conduct it, there's nothing to evaporate. The only rate of heat transfer is radiative heat transfer. That's the only thing that can go through a vacuum, right? So what do they do to the insides of these vacuum surfaces, right? They polish it, they make it silverized, right? So when you look inside a glass thermos, especially, you can see that silvering. It looks like a mirror. That's what they're doing, is they're preventing they're making the emissivity very small, okay? And when the emissivity is very small, then the rate of heat transfer is pretty small, okay? By the way, if they made these black surfaces that were good at radiating, your thermos would be almost worthless, okay? I mean, look at the difference between that and like something like this, like graphite carbon, right? Okay. And then the next thing, this thing here is our Stefan Boltzmann constant. And I'm saying Stefan because that's a German name and that's how he'd pronounce it, right? Notice that it's a very small number. And the reason for that is that the temperature to the fourth tends to be a really big number, right? But anyway, there it is. Notice it's watts per square meter per Kelvin to the fourth, and that works, right? This is the area, the radiative area. So it's the area that you're looking at, right? And then this is our the temperature in kelvins, of course, right? Now, sometimes we look at the heat transfer, and if we're out in space, we could sort of neglect the temperature of space, right? But sometimes we're actually off in some place, like we've got a box in a room, and the room is at one temperature, say T2, and the box is at T1. Right? And so what we'll do is we'll actually do this. We'll go T2 square root to the fourth minus T1 to the fourth. And this is an acknowledgement that although let's say this thing is hotter, T1 is hotter, right? It's radiating more heat to the surroundings, but the surroundings are also radiating heat to it, right? So it is a sort of a two-way street, right? Okay. Now what this means, by the way, is that if you're in a room and the walls are cold, let's say the air is warm, but the walls are cold, that is, you just turned the heat on, right? You're going to feel colder in that room because your rate of heat transfer is going to be fairly large via radiative heat transfer, okay? So the temperature of the walls is sort of important, and whether they're insulated, right, will make them warmer. An insulated house with the air at the same temperature as a non-insulated house, the insulated house feels warmer because the walls are warmer, okay? So sometimes it's a two-way street. This is heat radiated out, heat radiated back in, right? Okay. Let's take a look at some of these problems here. All right. A brick wall has been warmed by the sun and is at a temperature of 313 kelvins, right? I just made it like, I think that's 40 degrees, right? Celsius. So it's warm, feels warm to the touch, right? It's 13 meters long, 3 meters high. At what rate does it radiate heat to the surroundings, right? So the power is going to be the emissivity, right? T to the fourth, right? And then I figured it was a facing brick, right? And by the way, these are the emissivities at infrared wavelengths. The emissivities change with the wavelengths. So really, this is college level physics here, right? Okay, but we're just going to do, wow, that looks like all right, a gamete is what I was going to say. All right, so let's go here. So we got the power is 0.92. Okay, and then 5.67 times 10 to the minus eighth, and that's watts per square meter, Kelvin to the fourth, right? And then the area is going to be 13 meters by 3 meters. And that gives us our square meters, right? That cancels that out. And then it's 313 to the fourth. Don't forget, it's to the fourth, baby. So if you double a temperature in kelvins, right, you'll get 16 times the heat transfer. Okay, so 0.92 times 5.67 times 10 to the minus eighth. This is one of those constants you'll memorize, I promise. All right, not that you have to, times 13 times 3 times 313 raised to the fourth power. Wow, that's a lot. I'm getting 19525.98. Okay, so boy, that just seems like a lot of, that's watts, right? And then in kilowatts, that'd be 19.5 kilowatts. Okay, that seems like a lot, but understand that this wall, if we draw a picture of the wall, right, here's this wall. Here, okay, right. This wall is radiating that way, right? But the surroundings are also radiating heat back to the wall. So this is not actually the net rate of heat loss. It's just the rate at which it radiates out. And the net rate would be, we'd have to like figure out what the temperature of the surroundings is, right? And then we'd have to figure the difference between those two, okay? We'll do a problem that's like that. All right, let's look at the next one. An anodized aluminum sphere, 20 centimeters in radius, is used to radiate waste heat into space. So we're in a spaceship now, evidently, right? What temperature does it need to be to radiate 800 watts of heat, right? So you've got processes that generate heat on your space station, and if you're not losing it through the insulation, you need to like vent it into space. Nothing will conduct it. You can't use cooling fans because there's no air, so they just radiate the heat. Right, so we've got a sphere, right, and then notice that in the thing you've got the area of a sphere is 4 pi r squared, right? Okay, so we're going to go power is emissivity, Stefan Boltzmann, is that sigma? I don't even know, right? T to the fourth. Okay, so let's see. Our emissivity it's an anodized aluminum sphere. All right, so it's going to be 0.77. Oh wait, we got to set up an equation here. So 800 is equal to 0.77 times 5.67 times 10 to the minus eighth watts per square meter. This is watts. Kelvin to the fourth. All right, and then our area is going to be 4 pi times 0.2 squared, right? That's my area. And then the temperature is what we're solving for, right? So what temperature in kelvins does it need to be, right? This is higher mathematics. Basically, it's the cube root of this divided by all of this, right? Not the cube root, the quadic root. What is it? The fourth root. The second root, I'm going to go this divided by this and raise it to the 0.25. Okay, so parentheses. Oh wait, no, I can do it with a fraction. Parentheses, alpha f. Okay, so I'm going to go 800 in the numerator. And then in the denominator, I go 0.77 times 5.67 e minus 8 times 4 times pi times 0.2 squared. All right, and then right arrow, and then this. And then I'm going to raise that to the 0.25 to get rid of the fourth power. All right, and I get 436.95 kelvins, right, which is 437 kelvins, yeah? Okay, how hot would that be in Celsius? Minus 273.15. That'd be 163. It would hurt. It'd be hotter than boiling. 100 is boiling, right? Okay, degrees Celsius, right? All right. Yeah. All right. Let's look at the next one. Okay, so this is going to be one of those net heat flows, right? Transformer box has a surface area of 3.2 square meters. Here it is, and it's in a room that's it's at 39 degrees Celsius, right? Right, and the room is at 20 degrees Celsius, right? And then the emissivity of the box is 0.82. I just made that up. All right. So what we're going to do, first off, we got to turn these 39 degrees Celsius and 20 degrees Celsius into Kelvin. So this is 293.15 kelvins, and then 39 plus 273.15. 39 plus 273.15. Some kid asked me one other, do we have to put the 0.15? You do. Probably not. Okay, let's see. 312.15, right? Okay. Now what we're going to do is we're going to figure out the heat flow rate, and that's going to be heat flow out minus heat flow in, right? So the net power is going to be 0.82 times 5.67 times 10 to the minus 8th times 3.2. That's my area, right? Up to there, right? Times, and then the hot temperature is 312. And we're going to raise that to the fourth, and then we're going to go minus 0.82. Okay. Now you're like, what? Shouldn't we use that for the room? No, we're talking about the surface of this box, right? So we use the absorptivity. Really, is what this is. The absorptivity. This is emissivity. This is absorptivity, and they're the same number. Okay. All right. So 0.82 times 5.67 times 10 to the minus 8th times 3.2 times, and then this is 293.15. Now, what I'm secretly going to do with my calculator, because this is way too much typing, is I'm secretly going to go epsilon sigma area, and then I'm going to go T2 to the fourth minus T1 to the fourth, because I've done a lot of these problems. All right, so 0.82 times 5.67 E minus 8. So this is the heat output, and then the room is going to, of course, radiate heat back. I don't know if I explained that very well, right? Okay, so there's radiation goes both ways, right? Okay. Output, there's heat flow in, right? Or in this case, radiation, I guess, right? Okay, so let's see, times 3.2 times, and then I'm going to do a big parenthesis here. 312.15 to the fourth minus 293.15 to the fourth. Oh, whoops. All right. Let's see. Delete. All right, and then right arrow, minus. I forgot to do the minus. Okay. And then I'm going to go 293.15 raised to the fourth, and then I'm going to, oops. Okay, I think I'm good. Wank. Okay, and I'm getting, when I do that, I get 313.76 watts. That's the net heat flow, okay? Yeah. Now, let's think about this, right? That's probably the waste heat generated by this transformer. This transformer gets warmer and warmer than the room. It's going to do it until it's shedding heat at the same rate that the resistance in the wires is generating the heat, right? Transformers they waste some of the energy. I'm not talking about like Optimus Prime here. I'm talking about those little humming boxes that change high voltage to low voltage, or vice versa, right? That thing wastes heat at probably 314 watts, right? So it's going to heat up to some temperature so that it radiates heat at the same rate. It's losing heat at the same rate that it's gaining heat from the electricity, okay? If we increase the amount of heat wasted, the temperature would have to rise for it to be in equilibrium. That's kind of an interesting thing there. All right, I hope that helps.